We're now going to take a look at how nucleophilic substitution kind of fits into our idea of organic synthesis. And one of the things that we have to remember is there are a lot of nucleophiles. Now, I stated this at the very beginning of the chapter, but you certainly need to recognize that because there are a lot of nucleophiles, this means that there are many new functional groups that we now know how to synthesize. And just to kind of put that in perspective, you can see that based on this figure right here, right? So here in the middle I have some substrate with a leaving group, and the various types of nucleophiles that we may encounter. Hydroxide is a nucleophile. When hydroxide reacts with a substrate with a leaving group, you get alcohols. Um, Alkoxides, OR minus, when they react, they give you ethers. Mercaptide, SH minus, when it reacts, it gives you mercaptans or thiols. SR minus, alkyl thiolates, are also good nucleophiles. And when they react with a substrate with a leaving group, you get sulfides. And of course, we're going to see that you can actually take sulfides and react to get sulfonium ions, and I'll talk about that in just a little bit. Also, you can make amines from amide, the amide anion, or even ammonia. You can make secondary amines. You can make tertiary amines. You can make ammonium salts. You can make cyanides if you use cyanide as a nucleophile. So oftentimes these are called nitriles. You can make alkyl azides if you use N3, an azide salt. You can make other alkyl halides if you use a different halide as a substituent. You can even make acetylenes using the acetylide ion. And of course, lastly, something that we often don't think about is there is a way of making alkanes if you use hydride, H minus with 2 electrons as a nucleophile. So taking all of this into account, we can then start thinking about some of the ways that that we can synthesize new functional groups from uh, old functional groups, I guess you would say. So one of the things that we can do is we can use the acetylide ion as a nucleophile to synthesize alkynes. Now, how do we make the acetylide ion? Recall that if I take acetylene or a terminal alkyne, so in this particular case it would be a terminal alkyne. Acetylene is if the R group was hydrogen. And I know that a terminal alkyne is acidic. So if I react that with sodium amide in ammonia, the amide is a very strong base, and it's going to simply deprotonate the terminal hydrogen. So we can get deprotonation of that terminal hydrogen, and this results in what's called the acetylide ion. Now, acetylide ion can simply be HC triple bond C with a pair of electrons, but in general, it's a classification of anions where you could substitute H for any R group. And if in this process, of course, we get ammonia. Notice this is one of the reasons why we use ammonia as a solvent, because when NH2 deprotonates the terminal alkyne, it forms ammonia, which is simply now the solvent. Now the cool thing is that acetylide ions are good nucleophiles. They're very strong bases, so keep that in mind. That they're also very good nucleophiles. And therefore, if I take and I react my acetylide ion with an alkyl halide or a substrate that has a leaving group, the carbon, the acetylide carbon, can attack the R group and undergo an SN2 type mechanism and give you a new, what are called internal alkynes, right? So this is a way of making internal alkynes, or you could make terminal alkynes. If you start with acetylene, you can alkylate acetylene to get a terminal alkyne, and then you can take the terminal alkyne and you can deprotonate it, and you get a different type of acetylide ion, and then you can use that and make an internal alkyne. So an example of this would be, something like this. I have, let's see, 1, 2, 3, 4, 5. So this is one pentyne. One pentyne initially reacts with sodium amide and ammonia to deprotonate it. I get the acetylide ion of one pentyne, and then I'm going to react it with a primary alkyl bromide. Why a primary alkyl bromide? So remember I said this is an SN2 mechanism, and therefore for an SN2 mechanism to work, I really need a primary alkyl halide. Secondary alkyl halides, tertiary alkyl halides don't work very well. Again, one reason is a competing mechanism of elimination, which we'll get into later on. So in order to predict the product, you have to think about you're deprotonating the hydrogen on the end, and then it attacks that carbon, so the carbon on the right that is attached to that bromine. So how many carbons are we adding? 1, 2, 3, 4, 5. We're adding 5 carbons to the acetylide chain, and therefore we get 1, 2, 3, 4, 5 carbons on that chain. We form a internal alkyne. Internal alkyne simply means that there are 2 R groups on the triple bond, right? So this is one way of making all sorts of alkynes. Now, we also saw that sulfur could be used as a nucleophile in a variety of ways. We can take an alkyl halide and treat it with mercaptide, and in that process we form RSH, which is a thiol or a mercaptan. They have, same name, that means the same thing, so I typically call them thiols. Now, interestingly enough, a thiol is relatively acidic. I can take a thiol and I can treat it with sodium hydroxide and I can make an alkyl thiolate. And that alkyl thiolate is a good nucleophile. So I can take that alkyl thiolate here, this is an alkyl thiolate, and treat it with a halide or some substrate that has a good leaving group, and I can form R, S, R prime. So notice the prime simply means that R groups don't have to be the same, obviously. And so we form sulfides here, sulfides. RSR is a sulfide, or it's called a thioether, right? The thio derivative of an ether. Ether would be ROR primed. Now, interestingly enough, thioethers or sulfides the sulfur has 2 non-bonding pair of electrons on it, and therefore it can behave as a nucleophile. And if I take an alkyl halide and treat it with a sulfide, I can get a nucleophilic attack, right? Displacement of the leaving group, and it results in this RSR, right? So now I have 3 alkyl groups on that sulfur, and now the sulfur has a positive charge. This is called a sulfonium ion, Now, interestingly, we have a sulfide that reacts with an alkyl halide. The sulfide is a nucleophile, and it produces a sulfonium ion. Now the sulfur is electron deficient, which means what? That sulfonium ion is a good electrophile. Well, how can we use this to our advantage? We can use this to our advantage by taking sulfonium ions and treating them as what we call alkylating agents. So if I take a nucleophile, let's say an alkoxide ion, and I react it with a sulfonium ion, so the sulfur is electron deficient, but it's getting a little crowded in there, and therefore it's also a good leaving group, notice, where one of the R groups can be attacked, and then the a sulfide can actually come off as a leaving group. This is very similar to protonating an OH group and making water as a good leaving group, right? So I get attack at one of the alkyl groups, in this case, all three of them are methyl groups, um, and displacement of sulfide, and I end up with ROCH3 plus dimethyl sulfide. So what have I done? I've alkylated the alkoxide. And as a matter of fact, in biology, we have alkylating agents in our bodies. This is how adrenaline works, interestingly enough, right? So we've also seen oxygen can be a nucleophile as well, right? So again, alkoxides, RO minus, can be used as nucleophiles, and they make ethers when reacted with a substrate that has a good leaving group. So if I take an alkyl halide and I react it with an alkoxide, RO minus, then I get ROR. So ROR is an ether, ROR. And this type of setup here, where you're taking an alkyl halide and reacting with an alkoxide, has a name. It's called the Williamson ether synthesis. So it's so special that it actually has a name associated with it, and it's actually a pretty robust reaction, and so it's often used to make ethers. Now, because of that, we have to understand how to make alkoxides. And there are two main ways of making alkoxides. If you think about the alkoxide is a conjugate base of an alcohol. So the alcohol is the acid. And therefore, we have to treat the alcohol with a base. What base do we use? Well, we really oftentimes can't use like hydroxide because we know that simply sets up an equilibrium between water and the alcohol, and there's not a huge driving force to make the alkoxide. So we have to use a much stronger base. And one very good base that is often used is this. H minus. Remember, this is called a hydride. So we can use sodium hydride or potassium hydride salt. And the cool thing about this is a great way of making alkoxides. Why? Because the hydride acts as a base, removes that proton from the alcohol, and you produce the alkoxide salt, right? So now I have my alkoxide salt, and I've also added a proton to a hydride. And if you think about when you add a proton to a hydride, what do you get? You get hydrogen gas. And this is another driving force for the reaction. Hydrogen simply bubbles away, and based on Le Chatelier's principle, you shift the equilibrium to product formation. This is probably the easiest way of making alkoxides from alcohols and hydride. There is another way that's relatively common, and that is by taking an alcohol and reacting it with Na, so sodium metal, not sodium plus, but Na with its electron, sodium metal. Now, in order for this reaction to occur, you actually need two equivalents of alcohol to two equivalents, 2 moles of alcohol to 2 moles of sodium. The reason for this is you produce 2 moles of sodium alkoxide, but you also get hydrogen gas again. So this is another reason why sodium metal can be used. Essentially, you're donating an electron to the hydrogen, but you need 2 electrons for that process to occur and 2 hydrogens for that process to occur. And so this is a balanced equation here. Now, once we understand how to form alkoxide, again, I think the easiest way is to react an alcohol with a hydride. Now we can think about our Williamson ether synthesis. And you have to be careful in designing a synthesis, this Williamson ether synthesis of an ether. And the reason for that is because you know, you have to think about the alkyl halide and the alkoxide that you're going to use. If you think about it, here I have an ether where the two R groups are different from one another. And so if I have this scenario and I'm asked to make this particular ether, I can think about it in one of two pathways. Either I can make the ether from the blue alkoxide with the green alkyl halide, or I can make the ether from the blue alkyl halide and the green alkoxide. So oftentimes, and sometimes it doesn't matter, but oftentimes you have to think about the nature of the alkyl halide, and sometimes the nature of the alkoxide itself. What do I mean by that? Well, let's look at an example. Suppose I want to synthesize this molecule right here. So this is called tert-butyl methyl ether. Sometimes this is referred in industry as methyl tert-butyl ether, or MTBE, which is an additive in fuel. But the IUPAC name would be tert-butyl methyl ether. So now, let's say I want to make tert-butyl methyl ether. How would I go about doing it? Well, let's take a look at the two possible pathways. In the first one, let's say I use methoxide and I use tert-butyl bromide. So this is one possible pathway that I could take using methoxide or tert-butyl bromide. Now the other way would be to use methyl bromide and tert-butyl alkoxide. So in this step here, what do I have? Well, methoxide is a strong base, and tert-butyl bromide is a tertiary alkyl halide. And what do we know about substitution reactions of tertiary alkyl halides with a strong base? We know that they don't happen. So because the base won't attack the nucleophile. So, envisioning what's going to happen here, we have our alkoxide, it's coming in, our methoxide is coming in and trying to attack that alkyl halide, that tertiary alkyl halide, and so it's trying to get to that carbon, but it just can't do it. And therefore, no substitution occurs. And in effect, we'll see later on that you end up getting what's called elimination. We'll see how that process happens in the next chapter, right? So strong base with a tertiary alkyl halide does not promote substitution. And therefore, we have to look at the other pathway, using the tert-butyl alkoxide, tert-butoxide, with methyl bromide. So tert-butoxide here, reacting with methyl bromide. This is the best way, right? Because we have a strong base. The tert-butoxide is a strong base. We have methyl bromide, which is a methyl halide that has no hindrance to it whatsoever. And we'll see later on, it can't undergo elimination. So the only pathway that it can actually undertake is the substitution, an SN2 substitution reaction, and we form our tert-butyl methyl ether, right? So this is one process where we have to think about how we synthesize something from particular starting materials. Now, one of the cool things about the Williamson ether synthesis is that you can actually make cyclic ethers from an intramolecular Williamson ether synthesis. How does this type of reaction work? Well, let's say I have a compound that has a good leaving group, like a halide, and an alcohol. Well, what can I do with this reaction? I know, alcohols are okay nucleophiles. They're not very good nucleophiles, but if I treat that alcohol with a base, let's say potassium hydroxide, even better yet, maybe sodium hydride, then I can remove that proton, and now I have an alkoxide. The alkoxide can attack the carbon with the leaving group, and now I'm going to form a ring, and that ring looks like this. So, um, how do we go about trying to figure out the shape of that ring? Well, one of the best ways is to number uh, the reactant, right? So I start with the oxygen, always the oxygen, and I see that there's 1, 2, 3, 4, 5, 6. So that sixth carbon, it has the leaving group. So the oxygen, that one oxygen, is going to attack the sixth carbon, and therefore this is going to be a six-membered ring. And I can number this 1, 2, 3, 4, 5, 6. So I can make cyclic ethers this way. And a common cyclic ether is an epoxide. And this is one way of making epoxides. If I take, this is what is referred to as a vicinal halohydrin. A vicinal halohydrin. We'll learn how to make vicinal halohydrins in just a little bit. Notice it has an alcohol and it has an alkyl halide in it. So again, if I treat that alcohol with a base, like sodium hydroxide, I can deprotonate it, and then the oxygen can attack the carbon with the leaving group, and so I get an epoxide. So the way that this looks like, right, I'll show you, if I take and I deprotonate the alcohol, I get my alkoxide. So now that alkoxide can attack the carbon with the leaving group, the halide can come off, and I form my epoxide. Epoxides are simply cyclic ether. So this is a great way. That's typically how how epoxides are actually made using an intramolecular Williamson ether synthesis. The next atom I want to take a look at is nitrogen. Nitrogen being used as a nucleophile. And we see that amines are good nucleophiles, and they can displace a leaving group in an SN2 reaction. So I can use ammonia, and I can react it with methyl iodide, SN2 reaction, and what do I get there? I get an ammonium salt. So H3N CH3, so the nitrogen has a positive charge. And if I add another equivalent of ammonia, typically this is the case, which we'll find out in just a little bit, I can deprotonate that salt, and I get H2NCH3 plus ammonium as our new salt. But notice I form a primary amine. Now the interesting thing about this type of reaction is primary amines are better nucleophiles than ammonia. So I've just produced a good nucleophile. And if I don't have enough ammonia present, what's going to happen? Well, that good nucleophile, that methylamine, is going to react with my substrate with a good leaving group. So it's going to react with methyl iodide. And I'm going to get CH3, NH2, CH3. So now I've added another methyl group to my nitrogen. Again, I get a salt, but I can treat this with a base, an amine, and I end up with CH3, 2NH, so dimethylamine. And dimethylamine is a secondary amine. And guess what? Secondary amines are better nucleophiles than primary amines. And so this reaction continues. The secondary amine, dimethylamine, is going to react with methyl iodide to produce trimethylammonium salt. And the trimethylammonium salt is going to be deprotonated to give me trimethylamine. What have I made? I've made a tertiary amine now. And this process can even go a step further because tertiary amines are still nucleophiles. They have a pair of electrons on it, and therefore I can take that trimethylamine and react it with methyl iodide, and finally I get tetramethylammonium iodide. And this is what we refer to as a quaternary ammonium salt. Now obviously the reaction stops here because there's no more hydrogens that I can deprotonate, and this is one way of making ammonium salts, right? Alkyl ammonium salts. But in general, for a substitution reaction, this isn't a good way of making primary amines. Why? Because we tend to get over-alkylation. Now, an easy way to prevent over-alkylation is that we use ammonia or the amine that we're trying to add in a large excess, and that way our product can't react with the substrate with the leaving group. What does that look like? Well, oftentimes I'll abbreviate excess XS. So don't let that throw you. If you see in parentheses XS, that means that the reagent is in excess. So this is what it would look like. If I took iodocyclohexane and I reacted it with ammonia in excess, I would get cyclohexane amine. And that would be my major product. Now, obviously, cyclohexanamine could react with cyclohexyl iodide or iodocyclohexane. But if I have a large excess of ammonia in there, I'm going to limit that over-alkylation. Likewise, if I took 2-bromopentane and I reacted it with methylamine, again, in excess amounts, the methylamine can displace the halide, and I get this. So this is N-methylpentanamine, 2-pentanamine, N-methyl-2-pentanamine, right? So that's how we can use nitrogen as a nucleophile. Now, one last thing to think about is the stereochemistry of the reaction. And sometimes you have to consider what's happening to the stereochemistry in a reaction. Do you want to conserve the stereochemistry? Do you want a particular isomer over another one? So if so, how do you think about you have to think about the reaction mechanism and the pathway that you're going to get there. For example, let's say you were told to synthesize R2-azidopentane starting with S2-pentanol. Well, the first thing you have to do is you have to be able to draw R2-azidopentane and S2-pentanol. So let's take a look at how we would do that. Here we have R2-azidopentane. Remember, azido simply is the azide, that azide as a substrate. So this is an alkyl azide. Now I want to make R2-azidopentane from S2-pentanol. So this is S2-pentanol. If I draw it out and I think about the absolute configuration of this, right? Oxygen is 1 and the propyl group is 2 and the methyl group is 3, and I'm rotating in a clockwise fashion, but the hydrogen's coming out at me. So I reverse it, and so I get S. Now, I have to take a look. So notice the first thing that I have to do is I have to look at my product and I have to look at my reactant, what I want to start with, and I have to see what the difference is between the two. And the first thing that I notice is, well, I need to undergo an inversion of configuration, right? The azide has to come in from the opposite side of the OH. And what mechanism undergoes inversion? That's right, SN2. So I have to promote conditions that favor SN2. The other thing, though, that I have to take a look at is the OH. Is an OH group a good leaving group? It certainly is not a good leaving group, so I need to make that OH a better leaving group. And in the process, if I want inversion of configuration, I actually have to retain the stereochemistry of that OH so that when I go to do my substitution reaction, I have retained the stereochemistry so I can get inversion of configuration. So this is, these are some of the things that I have to take a look at. How do I make OH a better leaving group? Well, we've seen a couple of ways. We've seen that you can take alcohols and treat them with HBr or PBr3 or SOCl2, and you can make alkyl halides this way. Now, in all of those processes, what happens? Well, when I take the alcohol and I treat it with HBr, I protonate the OH, it comes off, it forms a carbocation. Bromide can come in from either side and attack the p orbital from either side, and therefore I get both stereochemical products. In other words, I get racemization. Is that what I want? No, I need to retain the stereochemistry of that stereogenic carbon before I undergo my substitution, because I now have to undergo a substitution with azide to form my alkyl azide. And if I react it with these two things, I'm not going to get the product that I desire. The other way is to take the alcohol and treat it with tosyl chloride, and I make a tosylate. Remember, when I make the tosylate, the oxygen is attacking the tosyl chloride, and I get a retention of configuration at that stereogenic center, right, at the stereogenic carbon. Now I have a good leaving group. I've retained the stereochemistry of my starting material, and now I can think about a substitution reaction. So what kind of substitution reaction do I need to think about? I need to think about an SN2 substitution reaction. So what am I going to do? Well, I'm going to take my now tosylate and I'm going to react it with sodium azide, because azide is the nucleophile that I need to make my alkyl azide. But I also want to promote SN2 mechanism. Azide is a good nucleophile. I have a secondary alkyl tosylate here. What other factor goes into thinking about promotion of an SN2? Solvent. So what kind of solvent do I want? I am going to use DMSO. Why am I going to use DMSO? Because DMSO is a polar aprotic solvent. Now I could have used another solvent as well. I could have used DMF. I could have used acetone. I could have used acetonitrile. Any of those solvents would work as long as they are polar aprotic. Could I have used water or ethanol or methanol? No, because that would promote SN1 mechanism. And therefore we see where the solvent now comes into play in reactions. And so now if I use DMSO, I'm going to promote SN2 substitution. The azide is going to come in from the opposite side of the tosylate, and I get my R2-azidopentane. And that is what we're going to be thinking about now in terms of synthesis. So you see that synthesis not only involves thinking about going from point A to point B, but sometimes it involves thinking about reaction conditions that favor one over the other.